Ladies and gentlemen, we are going to continue our discussion of nuclear magnetic resonance. And for this portion, we're basically going to simulate the machine. We're going to give the data that a machine that we bought could give us. That way you understand what that machine's telling you. Then when I just have the data, we can go backwards and figure out structures. That's the end of today, probably the beginning of tomorrow. We had a very good presentation just now. Took a little longer than normal. And I'll get this on video right now. If your presentation is 10 minutes, that's great. You've met the requirement for time. You can go a little over. I have no issues with that. Trying to cut it short, I can tell you're trying to cut it short. Don't do that. You're at a stage where you should be, trying to give more, not less. So to do this problem, you're answering 3 questions for every type of hydrogen in your molecule. I've labeled the types of hydrogen, and somebody carefully pointed out, and correctly pointed out, that I have 2 E's here, so let's fix that. We're going to need an F up here, and just add an F down there. You don't need to make your table bigger. Or just put the numbers across there. The 3 questions are, and I will interpret them here. This first column, I call this question, where is the peak? Like, what number does the peak have? And that's based on its chemical environment. So you watch the lecture videos and you hear me talking about things like shielding and de-shielding and inductive effects. I'm not going to talk about those now, but you should know that those words he just said, when you watch this video again, need to be learned. And basically, the 3 questions are, where's the peak? What pattern is the peak? So we have to learn how to draw the patterns and what they mean. That's multiplicity. And then the number of H's in the peak, which is the easiest question. I will answer it first. And then you'll know what I mean by types of hydrogen at the same time. Number of H's is how many hydrogens are in this molecule that are all exactly the same as each other. So this methyl here is different than these 2 methyls here, because this methyl is 1 away from a carbon with an OH, and this methyl is not 1 away from a carbon with an OH. They have a difference, that means they're different. So there are 3 that I'm going to call A. So here, easy, you put a 3 here. I'm going to do all of this column for both molecules right now. That 3 doesn't look so good. There's only one called B. I was going to write B there. There's only one called B. And there's 2 called C. Only one called D. How many of their E's are there? How many E's? 6. And F, there's only 1. That's the H on the alcohol. Moving over to the other molecule, don't be alarmed when I write 4 here. Take a second and try to figure out why I wrote 4 there. This is not the only CH2 attached to an alkene that has a CH2F on one side. I will point it out again. Here's a CH2 attached to an alkene attached to a CH2 with an F. I use the same word. The same CH2 has a CH3. The same CH2 has a CH3. The same CH2 goes to a C with a CH2 and then a carbonyl. The same CH2 goes to a C that is an alkene with a CH2 that's attached to a carbonyl. It's symmetrical is what I'm trying to say, right? I think you see the symmetry now. Here's a line of symmetry. Yeah, but don't talk about meso and stuff. I know you want to talk about meso. Don't talk about meso. There's no stereo centers here, okay? All right, but the idea is the same. So just basically do the A, B, C, D, E that's labeled and multiply by 2, right? So moving on to B, I guess there's 6 of them, right? And C, there's 4. If I forget to multiply by 2, please correct me before we move on. D, there seems to be 1, so that means 2. And E, there's 2, so that means 4. And that's the first question. How many H's? Well, it's the third, but it doesn't matter which order you do them in. Multiplicity is the tricky one. Let's do it last. The delta has to do with use the table given and match the type of hydrogen. It's type. It's not, you're never going to find these molecules on your exam, but the type. So methyl attached to a carbon looks like the second type here. There's a methyl, CH3. Just zooming in a little bit on the table. Methyl on a carbon is this one, A. So it will range from 0.8 to 1.0. Keep that in mind. 0.8 to 1.0. It's usually in there. What can take it closer to 1 is if there's electronegative atoms nearby, and you'll be reading about the inductive effect for that. That's what would bring it closer to 1. If it's nothing special, like just a normal old CH3 attached to pretty much just a hydrocarbon group, then that would be closer to 0.8, nothing special in there. So one of those CH3s, the A or the E, is very close to an oxygen. Which one is that? Which one's closer, A or E? A. So I'm going to make that the 1.0 and E 0.8. They're in the same category, but there's a range in the category. There's a range in every category. And if you have to decide which one's higher and which one's lower, the higher one will be closer to an electronegative atom, because that's de-shielding caused by electronegative atoms. You have to read about that. And then we're going to go to B. Now, don't be looking on these three entries for B, please, because the presence of the O dominates. That's an alcohol. HC alcohol is over here. H attached to C attached to alcohol. Do you see it right here? H attached to C, part of an alcohol. Don't worry about the number of H's in here. The O definitely has a much bigger effect. Look at 3.4 to 4.0. The O has a bigger effect than the number of carbons attached, doesn't it? Look, up here is where carbons attached has a very small effect. Please don't be using that to make your decisions if you have a functional group. There's the H attached to C that's part of an alcohol. Give me a number in that range. And, you know, if you're in the middle, that's safe, always. In fact, up here, if you gave me the same number twice, I'm going to give it to you. Right? You got the main category. That's the big thing. Coming down to the alcohols. How about 3.7? Sound good? So the B is the H attached to the C in the alcohol, and it's 3.7. And the C is in this category right here. And this was A, comma, E. And then here was E, no, wasn't E, was B, was it B? Yeah, B. And what about C? C's RCH2R. Give me 1.3. It's in the middle. And D, how many carbons are attached to D? Because D's not special. There's no functional, no electronegative atoms real close. So I just say there's 3 R groups attached to C, wouldn't you? Sorry, to D. There's a carbon group there and 2 more carbon groups. So I'm thinking right here, aren't you? Yeah, I like that one. So that's going to be D. And 1.6 sound good? 1.5? Either one. Something in the middle. And F is a very strange one. I'm just pointing out. And, you know, someday I'm going to edit these things. You can put this on your handout. It's always a broad peak. I'll explain the meaning of that when we actually have to draw the peak. But alcohol peaks are broad, and so are amine peaks. And if we have an amine peaks like right here, it's also broad. There's hydrogen bonding that's responsible for that. And these two in particular, and this one, which is kind of the same, you don't know this yet, but that's patterns. We don't know what that means, but maybe you want to make those additions to yours for when you're studying. And yeah, this one's broad too. OHs and NHs are broad. That means they're wide. And they're singlets. We don't know what that means. So singlets coming up. Broad. There's how many H's were there? There was alcohol. We got that here, 1H. Where is it going to be? Anywhere in this broad range. I mean, it's not going to be that broad, but pick a number in that range. Now, I always do alcohols at the end because keep in mind, you will be drawing the spectrum. And it's hard to draw things on top of other things. It's not impossible. Your life's better if you don't have to do that, right? Okay, so why don't we wait on that one and just pick a number we haven't used yet up here? Hey, this is the time because I've got all my numbers. I don't want to go outside the range I have here from 0.8 to 3.7 because that just makes my graph too wide. I'm thinking graphing 101 here too. So I want something in the middle here and not touching anything else. How about 2? 2 is great. Nothing at 2, right? Okay. So anywhere from 0.5 to 6. You got it there in front of you. And then I look at what I've already come up with, and I don't want to draw on top of something else. This is just practical. It's nothing chemistry. And so invent a number. And you're saying, why is that? Why can it be anywhere in there? Why does it change? Wow. Why? Well, the fact is that peak's position is dependent on hydrogen bonding. If it's highly concentrated, that means there's a lot of hydrogen bonding going on, and that will shift the peak one way. And if there's less hydrogen bonding, it'll shift the peak another way. Okay, so don't worry about using that as a prediction, but I'm just explaining. You never have to think about it again. Infrared spectroscopy, they're always broad for similar reasons. Yeah, so she's looking at lab stuff now. Yeah, in lab we look at infrared, and there's hydrogen bonding effects in infrared spectroscopy too for the same reason. Now multiplicity. Now that we're not doing multiplicity until we finish our ppms over here. We're getting more practice. Sadly, I got to shrink it down so I can see my molecule and the chart at the same time. I want to point out this category over here is called, well, it's already got it written. I'll highlight it in green. Highlight it in green. It's allylic, and I'm just going to use different color over here. That'd be A. Doesn't it fit the category of being on a C that's attached to an alkene? It's on a C that's attached to an alkene. That's what makes it allylic. Substantial jump for being allylic, isn't it? It goes higher than not being allylic. So give me something in that range, 1.6 to 2.6. 2 sounds pretty good. And B is just RCH3. That's the only RCH3 in my molecule, so I'm just going to go 0.9. I don't have to separate it from a different one that's in our RCH3. And C is a double category. I'm saving C till the end. And so is E. And they're both allylic. Wait, yeah, E is allylic too. I'm gonna get it backwards, unless I label them right here too. C and E. Okay, comma, and E is also alpha 2 carbonyl. Yes, this is a new alpha. But also, yes, chapter 16 has aldehydes and ketones, which have a carbonyl, which means we're talking about alpha hydrogens a lot on this test, and then even more on our next test. Okay. That's special if you're alpha to a carbonyl. That's down here. You see this? There's two of them. Alpha means one away from, this is a new alpha for you. That's our third or fourth. Shall we review the alphas we're supposed to know so far? Your first alpha was optical rotation. Chiral molecules will rotate plane polarized light in that direction for one enantiomer, and the other direction to the other enantiomer. That was your first alpha. Second alpha, I believe, was chapter 9. The carbon with the leaving group is called the alpha carbon. Carbon one away is called beta. You do elimination by taking a beta H and making a pi between alpha and beta. That was your second alpha you ever learned. Third alpha here. There's going to be like 9 by the end of 242. Yeah. Some of you said, oh, I remember sugars and stuff. We did alpha in biology and beta. Yeah, it's coming up. But our new one right now is if you're an alpha hydrogen, that means you live on an alpha carbon. And what's your position if you're an alpha carbon? Where are you in life? You're adjacent to what? Carbonyl. Okay. So we got that. And so alpha to carbonyl, the C double category is RCH2F. I'm just going to copy it from the chart. And once again, we're going to do those later because it's a combined effect. It's linear, which makes it easy. But this works. So we'll move on to D. D is nothing special, but it's called vinyl. D is called vinyl because it's right on the alkene, right? So I'm going to write the word vinyl over here. Vinyl. Here I should have written alpha, alpha. Vinyl terminal versus vinyl internal. What am I trying to say? In the middle of a chain is internal. Off to the end of a chain, which is not what we have here, right? No, this is in the middle of a chain. The better choice is the internal one, somewhere between 5 and 5.7. 5.4 looks like. That was D. Now time to talk about combined effects. So C, we got the two categories. Here's how you do the combined effects. We'll work on C first. The baseline for C, which would be same type of carbon with nothing special going on. So C is a CH2, and if nothing special was going on, it's just R groups. See, I copied the C, CH2RR. Now give me the middle of this category. RCH2R. It's 1.3. That's right. That's your baseline. Nothing special going on at 1.3. Now, to get that to be instead RCH2F, is that for C? It is for C. What would be your prediction there? RCH2F is right here. 4.4 to 4.5. Can we just call it one of those two numbers so I don't have to use a second decimal? 4.4. What was the jump that took you from the baseline up to the 4.4? I need the number. What did you add to 1.3 to get up to 4.4? Okay, now to get it to go the other direction and be also allylic, which means you're jumping to the allylic category. R, CH2, C, double C, allylic. What's the number for allylic? Just give me something in the middle of allylic. 2. 2 is nice. So it goes to 2. What's your jump to get you from 1.3 to 2? Plus 0.7. So your prediction, you start with baseline, 1.3, add both the red numbers and you're done. I told you, it's not hard. You just got to pick the right red numbers, right? And that looks like 3.8 to 5.1. Am I good? 2.0, 5.1, yeah. And that was for C. Put a star, because we had to do these things. You're gonna do the E one next. E starts off the same, right? Baselines are CH2. Let's see what smallest space we can do. That was 1.3, correct? And that goes to these two numbers, to allylic and to alpha. And allo we used before 2.0. We're still going to use that. That's jump 0.7. And alpha was 2. Which one's the better alpha prediction based on these two here? These are both alpha, right? Is it like the CH3 on a carbonyl, or is it a CH2 with more stuff on the carbonyl? That's the one, right? Yeah. So 2.4 is a better prediction. 2.4 was our prediction for alpha, which is a bump of 1.1. So your predict is 1.3 plus 1.7, plus 0.7, sorry, 0.7 plus 1.1. So 1.8, 5.1 again? It's because the alpha and the allele had similar predictions, I guess. Yeah. F, 5. That's not 5.1, it's 3.1. I was wondering why the numbers were the same and one of these was so much huger than the other. Yeah, because I can't add, apparently. You lose the skill over time. It's come a long way, too, because I started as a math major. Oh, yeah. Okay. Yeah, and so let's write that number down here, 3.1. And I think we're going to pause the video, and it'll be another activity for the multiplicity. And we'll actually do a new video. So next video, multiplicity column coming up.